Hey, ladies and gentlemen, how are we doing this afternoon? Hope you're doing good, or this morning, depending on what time of day you're watching this. You should be watching this on Wednesday. This is the exciting conclusion to Solving Trig Equations Part 1. This is Solving Trig Equations Part 2. Whew, we're going to cover some incredible stuff in this next half hour or so. I'm really excited about this. And you know what? I'm really loving making these videos. I think this is my calling. I might be leaving teaching and going into acting. What do you guys think? I think it's a good idea. All right. So, Solving Trig Equations Part 2. There's a couple things we have to kind of cover, and there's a couple things more than last time. First question is, of course, what do we do when we have a coefficient in front of the x? Like cosine of 2x equals 0. We're going to try and solve cosine of 2x equals 0. We can figure out what 2x is. We can solve this, say 2x would equal, well, when is the cosine 0? I got to think for a second. Cosine is 0 on the unit circle. Cosine is 0 straight up and straight down. And so I can say 2x would equal pi over 2, or 2x would equal 3 pi over 2. Both of those things are correct. Both those are correct. But again, that solves for 2x. When we have to solve for x, not for 2x, but for x. So we can get to here from this statement here that leads to these two. But we really want to find out what x is. So let's go over to here. I gave myself some more room on this side, knowing I was going to need a little more room. So over on this side, I'm going to go ahead and say 2x equals pi over 2. And then we also have or 2x equals 3 pi over 2. Now remember, we are still trying to solve for x over all the numbers, not just 0 to 2 pi. So before I do anything more, I'm going to say 2x equals pi over 2 plus 2n pi. Plus 2n. Whoops, I do that every time. Plus 2n pi. And 2x equals 3 pi over 2 plus 2n pi. Okay, that takes care of the wrapping. But I do want to find out what x is, not what 2x is. And so I just divide this entire equation by 2. Divide both sides by 2. If we do that, divide that by 2, and then divide that by 2, and that by 2. And if we do that, I'm going to change colors so we can see where the next line is. If I do that, I get x equals pi over 2 divided by 2. That's pi over 4. And then n pi divided by 2 is just plus n pi. And then down here on the second one, we're going to divide that whole thing by 2 as well. Divide that thing by 2 to get x by itself. We got that, and that. And we got x on the left. X equals now 3 pi over 2 divided by 2. Well, that's 3 pi over 2 times 1/2. And so that's 3 pi over 4. And then 2 plus 2n pi divided by 2. That would be just plus n pi. So we got it right there. These are the answers. Now I do want to point something out though, because something's kind of neat here, kind of cool, kind of far out. Pi over 4 plus n pi would give me like pi over 4, 5 pi over 4, 9 pi over 4, etc. 3 pi over 4 plus n pi would give me 3 pi over 4, 7 pi over 4, 11 pi over 4. But if I went like this, pi over 4 plus n pi over 2, just added like pi's over 2, then I would get pi over 4. And if I added pi over 2 to it, I'd get 3 pi over 4. And if I added pi over 2 more to it, I would get 5 pi over 4. And if I added pi over 2 again, I would get 7 pi over 4. So what I'm trying to say is you can get this pi over 4 plus n pi and 3 pi over 4 plus n pi. You can get all that right here. This includes all of that. And that was a better way to say that answer. All right, now we're going to do another example that is a problem that was due yesterday at like, I don't know, midnight, whatever time I said that assignment was due. And it was number 24, the last one. The last one, this one here. And it uses that idea we just did. So if I have cosine of 2x times 2 cosine x plus 1 equals 0, we're going to go zero product property on this, and we get cosine 2x equals 0. And then if we do this one, we get 2 cosine x plus 1 equals 0. Well, this guy, we just solved. And that's actually, right, I just ripped my paper, did it again. That solution is right there. X equals pi over 4 plus n pi over 2. So this one, x equals pi over 4 plus n pi over 2. But this guy over here, we got to get cosine x by itself. So I'm going to say cosine x equals negative 1/2. And then I got to figure out where is cosine x negative 1/2. Cosine is negative, first of all, it's a second or third quadrant. That's where cosine is negative. And cosine is a half at the high one. And the high one is pi over 3. And so it's going to be, let's see, I mean, second and third quadrant for pi over 3. And that would be, second quadrant would be 2 pi over 3. Third quadrant would be 4 pi over 3. So your answers would be x equals 2 pi over 3 or 4 pi over 3. That's where cosine is negative 1/2. So we'd have 2 pi over 3, 4 pi over 3, and we also have to remember we're wrapping this, and so it'd be 2 pi over 3 plus n plus 2n pi, 4 pi over 3 plus 2n pi, and then pi over 4 plus n pi over 2. Whew, that's a lot of work. That was the last problem from the homework that was due yesterday, all right? So the key, the main idea to this example, these examples, are what do we do when we have a coefficient? And what the coefficient does is it tells us how many times we're going to have to wrap. All right. We're going to do more examples with the coefficient when we are doing problems that require us to just go 0 to 2 pi. Just going to go 0 to 2 pi. I'm stepping on my paper again. All right, we're looking at this example. The big change now, the big thing that's different about this example from the previous ones is we are just solving over 0 to 2 pi. We're not going wrappy forever, but there will be examples when we do have to kind of take wrapping into account, and we'll see that when we get to it. One thing I do want to make perfectly clear, unless the directions tell you to use degrees, you always solve trig equations in radians and with respect to pi, always in terms of pi and radians. Now, sometimes the directions will say, use your calculator to give a decimal approximation. That's fine. Then you follow the directions. But if they don't tell you that, then you always answer in terms of pi and you're in radians. Always. Okay, so this example, we're trying to solve this equation over 0 to 2 pi. And we have 3 tangent cubed equals tangent of x. Now, one thing you might think you should do right off the bat is, hey, let's divide both sides by tangent. Well, if we do that, then we lose any answer that would have been tangent of x equals 0. Whenever tangent of x equals 0, we would lose it. It would not be part of the solution anymore. So what I'm telling you right now, don't ever divide both sides of the equation by a trig ratio. If you do that, what you're doing is you're eliminating the possibility of that trig ratio being 0. So instead, we're going to subtract tangent from both sides, and then we're going to factor. We're going to do 2 things. We're going to subtract tangent from both sides, and we're going to factor. If I subtract tangent x from both sides, I have 3 tangent cubed x minus tangent x is equal to 0. Okay? Now I say, hey, I got a greatest common factor. I got tangent x. That's a greatest common factor. I can factor tangent x out. And I get tangent of x times 3 tangent squared of x minus 1 equals 0. Hey, wow, cool. Now I can use a zero product property and say tangent of x equals 0. Or this expression equals 0. I'm going to kind of do 2 things at once because I got to save room on my paper. If this equals 0, that means the tangent squared of x equals 1/3. I just added 1 and divided by 3. That would mean that the tangent of x equals plus or minus the square root of 3/3. So I got the tangent of x equals 0, and I got tangent of x equals plus or minus the square root of 3/3. All right, let's do tangent of x equals 0 first. Let's figure that one out. Tangent of x equals 0. Remember, tangent is 0 when the sine is 0, because tangent is defined as sine divided by cosine. So I think, when is tangent equal to 0? It's when sine is 0, and sine is 0 at, let me think, sine is 0. Oh, sine is 0 at 0 and pi. 0 and pi, when we're on the x-axis, that's when sine is 0. So I have two solutions on this one. So x would equal 0, or x would equal pi on that one. Okay, now on this one, I got tangent of x equals plus or minus root 3/3. So plus or minus, that tells me I'm going to have 4 answers. I'm going to have one solution in each of the 4 quadrants, okay? So I just got to think, when is tangent root 3/3? I definitely recognize that. I definitely recognize root 3/3. Okay, that's definitely, okay, that's when you have 1/2 on top and root 3/2 on bottom, and you rationalize the denominator, keep change, flip, blah, blah, blah. You get root 3/3. So I need sine to be 1/2. Sine is 1/2 at the lower of those angles, and the lower one is pi/6. And so we're going to have pi/6 is our first quadrant, and then we have the corresponding angle in the second quadrant, which is 5 pi/6. And then we have the third quadrant angle, which will be 7 pi/6. And then in the fourth quadrant, we have 11 pi/6. So these are our 6 solutions to this problem. This is number 27 on page 482, right smack dab in the middle of the next assignment that you have to work out. Now, one thing I do want to point out right here, if we had foolishly started off, if we had incorrectly and ill-advisedly divided this thing by tangent x to start with, if we had done that, which is bad, we should not have done that, then our next step would have been 3 tangent squared of x equals 1. And then if we divide both sides by 3, we get tangent squared of x equals 1/3, which is right here, right? We would have been right here. We would have lost this. This would have been gone. We would not have found these two solutions if we had made this grievous error of dividing both sides by tangent x. Don't do that, because tangent x could be equal to 0, and we don't divide an equation by 0. All right, hope I got that across to you. Don't divide both sides by a trig ratio. Bad. Okay. All right, next, we're going to do another example. This is, I like to call this example my example with wrapping. Now, I know you probably want me to bust into some Run DMC, like my Adidas. I'm going to wrap. Right? That's a different kind of wrapping. Instead, we're talking about wrapping around the unit circle. If you can picture like wrapping, if I'm at pi/3, for instance, and I'm going to wrap around the unit circle, I'm going to add 2 pi, right? 2 pi, and get, let's see, pi/3 plus 2 pi, that'd be 7 pi/3. And if I add 2 pi to that, 13 pi/3. Yeah, okay? That's what I mean by wrapping. All right, this is an example. We're going to do 2 examples with wrapping. All right, so cotangent of 3x equals 1. So this, again, we're just going from 0 to 2 pi. All these problems are 0 to 2 pi. Cotangent of 3x equals 1. That 3 tells me I'm going to be wrapping 3 times. Okay, I'm going to wrap 3 times. All right, so I'm going to say 3x equals. All right, so let's see. When is the cotangent of an angle equal to 1? Well, that's not very hard, because the cotangent equals 1 exactly when the tangent equals 1. Okay? That's not a trick. Because if sine and cosine are equal to each other, then the cotangent and the tangent are both equal to 1. Okay, so the cotangent in the first quadrant, the cotangent equals 1 at pi/4. So that would be 3x equals pi/4. That's cool. But what I'm going to end up doing to get x by itself is dividing by 3. We're going to divide both sides by 3 here in a minute. That's cool. But I got to remember that if I'm going to divide by 3, this is confusing. I know this is confusing. And I'm restricted to going from 0 to 2 pi. If I go from 0 to 6 pi off the bat, right off the bat, then when I divide by 3, that would be restricting it to 0 to 2 pi. Because we're looking for all the solutions from 0 to 2 pi. So that 3 is going to tell me, okay, I'm going to go plus 2 pi here. I'm going to add 2 pi to pi over 4, because that'll be one wrap. 2 pi plus pi over 4 would be, I'm going to add 8 pi over 4. That's going to be 9 pi over 4. Okay? And I'm going to wrap one more time. I've wrapped once, and now I'm going to wrap again, and the next one's going to be 17 pi over 4. Now also, where else? What other quadrant is cotangent positive? Okay, good. The third quadrant. So the cotangent would be equal to 1 in the third quadrant. It would be also, I think it would be at 5 pi over 4. So you can picture 5 pi over 4 in the third quadrant. And then we're also going to wrap. We're going to go 2 more times around. We're on the one time around, and then we're going to go whoosh, another time, and then another time around. And we're going to get, 5 pi over 4 plus 8 pi over 4 is going to be 13 pi over 4. And then plus 8 pi over 4 is going to be 21 pi over 4. So 3x is all these, all 6 of those. So x would equal, now we just take each one of these solutions for 3x and divide it by 3. We're going to divide it by 3. Okay, watch. Pi over 4 divided by 3 is pi over 12. 9 pi over 4 divided by 3 is 3 pi over 4. 17 pi over 4 divided by 3 is 17 pi over 12. 5 pi over 4 divided by 3 is 5 pi over 12. Keep going here. 13 pi over 4 divided by 3 is 13 pi over 12. And then 21 pi over 4 divided by 3 is 7 pi over 4. All right, so here's the answers. Kind of crazy, kind of wacky looking answers, but those are correct. Let me recap again what in the world we were doing on that problem, okay? I know this is very confusing. It's a very hard topic to really get your mind wrapped around. We figured out that the cotangent of 3x equaled 1, then 3x would be equal to pi over 4, 9 pi over 4, 17 pi over 4, 5 pi over 4, 13 pi over 4, 21 pi over 4. Now let me back up a little bit. The easy answers are right here. Those are the easy answers. Okay, that's the first quadrant and the third quadrant. But then if you wrap around, you get to here and you get to here. If you wrap this around, you get to here and you get to here. And the reason we're wrapping around, because when we're done, last step, we're going to divide by 3. And we want all the answers, all the possible values of x, that when I plug it in here, it would work. We would end up with a cotangent of 1. So let's just real quick, arbitrarily, pick one of these crazy answers. Let's pick this one. Just for fun. Let's pick the cotangent. Let's do cotangent of 3 times 7 pi over 4. And let's just see what happens. Sort of a check. We're going to just check this one answer right here. So we have the cotangent of 3 times 7 pi over 4. Well, that would be the cotangent of 21 pi over 4. 21 pi over 4. Okay, now I got to think about like reference angles and stuff. So 21 pi over 4, 21 pi over 4 is like, let's see, not quite, so 5, 4 goes into 21 5 times, so it's like 5 1/4 pi. Oh, so 5 pi would be like, think about this. There's 2 pi, 4 pi, 5 pi, and then another 1/4 pi would be here. Okay, so we're looking at the cotangent of the angle in the third quadrant, whose reference angle is pi over 4. Okay, that's one. All right. That's why it works. Now, if I'd have gone one more wrap, I wouldn't be there anymore. I'd be outside of the 0 to 2 pi range. I would be too high. All right, so we're going to do another example with wrapping in just a second. And hopefully you'll understand this. I thought we were going to do another example of wrapping. I had another example of wrapping. Let me get it up there real quick. I think it may be gone. I got to find my other example with wrapping. All right. Let's do it. I know I have it written down. I didn't make my table for it. There it is. Cosecant of 4x equals 2 over the square root of 3. I thought I had that one. Nope. Okay. We're going to do it right now. The cosecant is another example of wrapping. Make sure it's under here. Ah, I found it. I knew I had it. All right. All right, good. So here's the second example with wrapping. Cosecant of 4x equals 2 divided by the square root of 3. All right, well, cosecant. Right away, I don't care about the cosecant. I care about the sine. So let's change this to the sine of 4x equals the square root of 3 over 2. Now we're talking. All right, so 4, that tells me I'm going to wrap 4 times. Because the last thing I'm going to do to solve this problem is divide through by 4 to get that x by itself. So I'm going to say 4x equals, all right, so when is the sine root 3 over 2? When's the sine root 3 over 2? That's the high one. The high one's pi over 3. Yes. And so 4x equals pi over 3, or 4x equals, when's the other time that the sine is root 3 over 2? It's the second quadrant, right? Second quadrant, and that would be 2 pi over 3. Very good. Now, I got to wrap it 4 times. Each of these got to wrap 4 times, and then I got to divide the whole thing by 4. I'm going to add 2 pi 3 times. So it's to be once, twice, it'd be wrapped once, twice, 3 times, 4 times. So we're going to add 2 pi to pi over 3, and we're going to get, let's see, that's 6 pi over 3 plus pi over 3. That's 7 pi over 3. And then we're going to add 6 pi over 3 again. We're going to get 13 pi over 3. And then we're going to get 6 pi, it's 19 pi over 3. And then down here, we're going to add 6 pi over 3. We're going to get 8 pi over 3. We're going to get 14 pi over 3. And we're going to get 20 pi over 3. We're going to divide all these guys now. We're going to divide everything by 4 because we're trying to get x by itself. And so our solutions, I'm going to list them out down here. I'm going to say pi over 3 divided by 4 is pi over 12. 7 pi over 3 divided by 4 is 7 pi over 12. 13 pi over 3 divided by 4 is 13 pi over 12. 19 pi over 3 divided by 4 is 19 pi over 12. 2 pi over 3 divided by 4. Now it's going to get a little harder because we can reduce these numerators. 2 pi over 3 divided by 4 is 2 pi over 12, which is pi over 6. 8 pi over 3 divided by 4 is 2 pi over 3. That one was easy. I got to be careful on the right of my wall. 14 pi over 3 divided by 4 is, okay, that's going to be 14 pi over 12, which is 7 pi over 6. And my last one, 20 pi over 3 divided by 4, that's 5 pi over 3. Okay. Whew! So that's the answer. That, whew, looked like a pretty easy problem, but there was a lot of thinking involved. We really had to noodle through, had to wrap it, and had to divide by 4. Good stuff, good stuff. All right, this next one I call just an example using your brain. Example using your brain. And I had fun with my n there. I made my n backwards just for fun, just to be goofy. All right, so example using your brain. All right, well, one way you could do it, you go, okay, Let's see, it's convenient form of 1, multiplied by 1 plus cosine squared, blah, blah, blah. You could do all that. You really could. But instead, just think about it like this. I got a number divided by another number, and it equals 0. Well, when is one number divided by another number equal to 0? No, not when the bottom is 0. Right, when the numerator is 0. When the numerator equals 0. So this, I can just change this to 1 plus cosine of x equals 0 and solve that. Ha ha! We have cosine of x equals -1, and when cosine is -1, we're at pi. So this is x equals pi. Ta-da! That's it. That's the end of the story. Now, you really could have multiplied through by 1 plus cosine x if you wanted to, top and bottom. And then, you do a lot of work, but you still end up right here. This is what I call just using your brain. Just use your brain. Sometimes, just use your brain. And you can solve the problem pretty easily. All right. This next example, I gave myself extra room over here. No, I didn't. Oh, yeah, I did. But I have that up there first. All right. So this is an example using an identity. Now, we have both secant squared and tangent squared in the same problem. And that's no good. Like, I don't want to go too far with having multiple trig ratios in the same problem. I want to get it all back to either all sines or all cosines or all tangents or all secants. You get the idea. So right now I got to think, what can I do to this guy to get either all secants or all tangents? All right, so I'll leave this over here. Hopefully you're looking at this, our Pythagorean identities that would be on the wall, right? For our poster to look at, my Amazon poster here. But okay, so this is the one I think I want to use. I want to look at secant squared right there. I see that secant squared, and I'm going to change it to 1 plus tangent. I'm going to take this and put it in right there. Okay, so I'm going to have 1 plus, I have 2 times 1 plus tangent squared x plus tangent squared x minus 3 equals 0. Whew! No more secant squared. So now let's distribute this 2. Watch this fancy math right here, everybody. Is 2 plus 2 tangent squared x plus tangent squared x minus 3 equals 0. Now I got this. I can combine my like terms here. If I do that, I got 3 tangent squared x. I got 2 minus 3. So minus 1. 2 minus 3 is minus 1 equals 0. And then if I get the tangent squared by itself, I got tangent squared x equals 1/3. Okay? I get there. I gave myself some more room over here. Yeah. More room to work out number 39, so I knew that it was a long one. All right, so we're going to go over here. And let's take the square root of both sides. Now, I've noticed when I'm checking paper, that some of us are getting a little lazy and we're not indicating the plus or minus. Not indicating the plus or minus right here. So you're losing half your solutions, okay? So you got to make sure you do that. Also, tangent of x equals plus or minus root 3 over 3. And now I just got to think, well, where is tangent root 3 over 3? That's when the sine's 1/2. Sine's 1/2 at pi over 6. Okay. So x would be equal to pi over 6. Okay. But it's plus or minus. So it could be in the second quadrant too. Oh, 5 pi over 6. Okay. And then also the third quadrant, because that's where tangent's positive. So 7 pi over 6. And of course in the fourth quadrant, 11 pi over 6. So recapping this, the idea behind this problem is I tried to get rid of that secant squared. I said, okay, I want to use my trig identities that Mr. Wilding made me learn. And I did all those identities. I verified identities and verified identities until I got used to them. Whew! And that was the reason why we were doing those verifying identities. One of the reasons is so we can solve trig equations. And also, when you're in calculus, you're going to do some trig substitutions, which are going to be helpful as well. All right, so I think we're ready to summarize. Yes, summarize what I wanted you guys to get from today's exciting part 2 lesson. 3 things I wanted you guys to get at it today. First of all, the coefficient, that darn coefficient, that tells us how many times we're going to wrap around the unit circle, how many times we have to add 2 pi before we end up dividing by that coefficient. That's number 1 thing to learn. Second thing was when we're solving these guys, look to factor how we spent a month factoring back in the beginning of the year so that we'll be proficient by now. We never divide by a trig ratio because then we lose our roots. We're going to lose possible roots. And lastly, look to make substitutions based on your trig identities. The most common substitution that you're going to use probably, or the most common identities you're going to use are the Pythagorean identities. They're always very helpful. And we want to try and get it down to just one trig ratio. We don't want to have a sine and a cosine, for instance, in the same problem. We want to have all sines or all cosines. Or all tangents or all secants, but not a whole bunch of all of them. Okay. Hopefully that's helpful to you. And you have to watch this video before you try the problems, guys. I'm not lying. There are some really hard problems I'm assigning you right now, and this video is going to help you. I might even recommend watching the video, then doing the work, and then going back and watching the video again, because it's well, one reason that will increase the number of views on my YouTube page, which I'm very excited about, but also it'll help you learn the math. Okay, goodbye. I'll talk to you soon.